Tom, for a wonderful introduction.
Yeah, right.
Everything he said is absolutely true. We're extraordinarily distinguished. With that out of the way, I want to begin this conversation tonight with a question of why are we here? And by that I don't mean like why we're here in Vintage Forum. We all know why we're here, but why are we here more broadly? What is the sequence of events that led to the emergence of advanced life on this planet? And of course, in some sense, this is a biological question, right? You could imagine asking that question and answering it in a biological fashion. But just as the, say, researcher at Caltech does not really happen without the context of the institute itself, I would argue that the more fundamental question, or an equally fundamental question, is to ask the question of what are the physical processes, what are the astrophysical, chemical processes that lead to the emergence of environments in which life can form. So with that said, we will move away from the picture of the Chinese balloon here and take a broad look at the solar system. After all, the Earth is not isolated, right? The Earth is not the only object that orbits the sun, and the architecture of the solar system looks like this, with the planets indeed on this diagram shown to scale, right? So this here is the sun. We have Mercury, Venus, Earth, and Mars. A few asteroids in between, and then as we move away, we have Jupiter. Jupiter is the most massive planet in the solar system, clocking in at 300 Earth masses, followed by Saturn at 90 Earth masses, and the two somewhat smaller ice giants, Uranus and Neptune, at 17 each. I should mention that beyond Neptune, there's also a collection of icy debris my distinguished colleague here discovered, all the important ones out here. And if you were to go far beyond what the projector allows us to do, you would, as Tom mentioned, find Planet 9 well beyond the water over there. So I like this picture because it demonstrates to you that the solar system, right, structurally, really is subdivided into two groups of planets. There's kind of small things that are rocky, right, that have very thin atmospheres, that are close to the sun, and if you go far beyond, there's really, really large objects. But at the same time, this particular picture is deceptive, because what it hides is the orbital architecture. So let's take a look at that, okay? So here we have the sun in the center, Mercury, Venus, Earth, Mars. Actually, if you look very closely, my house is right there. And we have Jupiter, Saturn, Uranus, and Neptune. Jupiter is 5 times as far away from the sun as is the Earth, and Saturn is about 10, Uranus is about 20, Neptune's at 30. Okay, and you really begin to appreciate the fact that the terrestrial group of our planets really is quite close. It's this compact sequence of rocks that live seemingly much, much closer to the sun than do the giants, right? For the longest time, this was the blueprint of planetary systems, right? Dating back 400 years, people have tried to look for planets around other stars with this as the blueprint. And if you do that, there's really 2 ways that you go about doing that search. Number one, you look for the most massive things. You would look for the analogs of Jupiter orbiting other stars, and you would look for that by kind of the slight periodic reddening of their host stars with a period of about 10 years, the time scale it takes for Jupiter to revolve around the sun once. Alternatively, if you're trying to find something like Mercury, you would just stare at the night sky and measure how bright the stars are in hopes of measuring a dip where a planet goes and eclipses one right? Those are the two methods that you can use to try and find planets around other stars. The problem, even though people have attempted something like this for about 400 years, it hasn't been until the last 30 that the technology of telescopes came into sharper focus where you could actually carry out this exercise. So starting with 1995, okay, now to be clear, this is after Nirvana broke up, but before Britney Spears made it big, okay, so that's give you a scale, okay? So during that decade, right, we found the first planet orbiting a sun-like star. And since then, right, we have experienced an explosion of this activity, right? This diagram here shows you all of the planets that we have discovered to date. We have approximately 5,000 of them now in the galactic planetary census. And looking at this diagram alone, ignoring this text, which is typeset at 0.1 font for your readability, you know that there's the whole spectrum of planetary objects. There's big ones with rings, there's kind of smaller, kind of Neptune-sized things, there's a bunch of rocky-looking worlds. So you have the full spectrum of planetary system. But just like that picture of the solar system, which didn't show you the orbits to scale, this picture is misleading, okay? Because it doesn't show you where the orbits are. So let's take a look at that again. Okay, so this is projecting all the planets that we found to date around their host star. Of course, they don't all orbit the same star, right? They all orbit their own individual stars, but putting them all in orbit of a single object for just visualization, this is what the currently known galactic planetary census looks like. And if you're a careful observer, you might be like, that star looks really big, right? I'm not sure that it looks big compared to the planets. It's the same, question as like, are children small or are they just far away? Right? No, they're small. So this is the staggering thing that we found out. Okay? This is the galactic planetary census. All the planets we know of today. This is the orbit of Mercury, the closest thing we have to the sun in the solar system. Okay? Venus, Earth, and so on. Right? We're not the average outcome, clearly. Most of the things we found to date complete a single revolution around their host stars, and the